Hey everyone, welcome back. So in this video, we shall take a look at the partial autocorrelation function. So before we move on to partial autocorrelation function, we shall see why do we need this new function when we already have the autocorrelation function, right? So this is the ACF for the MAQ process. This is the ACF for the ARMA11 process, and this is the ACF for the AR1 process. So you can see that for MAQ process, for lags greater than Q, it is 0. That, however, does not hold true for ARMA or ARMA11 or the AR1 process. And this motivates the need for the partial autocorrelation function or the PACF, right? So this cutting off of the ACF after Q lags is a signature of MAQ process. For MA2 process, the ACF will cut off after 2 lags. For MA3, it will cut off after 3 lags, and so on. However, the ACF tells us very little about the orders of the ARMA or the AR process. So our whole goal is to determine or construct a function that will behave like the ACF does for the MA models, right? So basically we want a function that will cut off after lag 3 for AR3 models, will cut off after lag 4 for AR4 models, and so on. And that brings us to the partial autocorrelation function or the PACF. So before we study what this PACF is, a little bit of regression stuff. So suppose you want to predict xt plus 1 based on xt, and we're going to use a linear model, that is, we are going to use regression. We assume that xt is stationary and has 0 mean. We know that, right? So basically xt plus 1 hat, that's the predicted value of xt plus 1, is equal to beta times xt, and we need to determine beta, right? So in linear regression, right, this is the linear function of xt, and I want to find beta to predict this xt plus 1 hat. So we are going to find beta that minimizes this, right? So this is what we want to predict, and beta xt is the predicted value. We want to minimize this error, right? So this is the error, prediction error, and we want to minimize this prediction error. So this prediction error, I'm calling it as L. So that is, so the goal is to obtain beta that minimizes L. Great, we know how to do that. Differentiate with respect to beta, equate to 0, and solve for beta. So this is what we get. We get beta is correlation at lag 1. So the predicted value of xt plus 1 is rho 1 times xt. Now suppose we want to do the opposite, that is, we want to predict xt based on xt plus 1. Now I know you might think, why would we ever want to predict a current value based on the future value? But just you'll see why we're looking at this later on in the video, okay? So again, xt is stationary, 0 mean, and we want to find beta such, right, that minimizes this prediction error, right? So now I have xt here and xt plus 1 here. So we do the same thing. So this is the prediction error L, differentiate with respect to beta, equate to 0, solve for beta, and surprise, surprise, we get the same value for beta again, right? That's rho 1. So basically, predicted value of xt is rho 1 times xt plus 1. So just a quick summary. So if I want to predict xt plus a future value, right, xt plus 1 based on xt, my beta is rho 1. And if I want to predict xt based on 1 time step in the future, my beta is again rho 1. Can we generalize this, right? So if we do this regression, right, so this is predicting xt plus h, and so at not one time point in the future, but at some h points in the future based on all of these points, right? So beta 1 times 1 time step back, 2 times 2 time step back, plus h minus 1 times h minus 1 time steps back. You can write this more succinctly in this way. So this is one regression and this is the other regression. So like I have these two regressions where I'm predicting future based on past and past based on future, or right? So future based on past, I'm going to do past based on future here. So xt, beta 1, 1 time step ahead, beta 2, 2 time steps ahead, and so on. So note that I'm using the same betas. So here we saw that this beta value ended up being the same. We didn't know it at the start, but it ended up being the same. And it will also hold true here. So you don't know this now, but I'm using the same notations because these betas will end up matching, or they will end up being the same. So I will be obtaining what these betas look like in this video, and you will be obtaining what betas look like for this equation as a homework or as an assignment, and you will see that the results for both of these will be the same. Okay, all right, so let's see. So we want to determine betas, that's the goal. So again, we want to minimize the prediction error, that's the prediction error L. So now we have, so in the previous case we just had one beta, now we have h minus 1, many more betas. Mathematically nothing changes a whole lot, right? So now I'm going to differentiate with respect to each of the betas one by one. So I'm going to differentiate with respect to beta 1, beta 2, and so on. However, it's rather tedious, right, to write each of these derivatives. So this is a general way of writing it. So derivative of L with respect to beta k, where k can take any of these values. K can be 1, 2, anywhere, or it can be h minus 1. So derivative of L with respect to beta k has this form. So remember, we are differentiating with respect to only one beta here, right? Beta k, one specific beta. So that's not hard to do. Then we differentiate with respect to beta k equate to 0. Simplify and simplify further. This is what we get. Okay. So what I have here, so remember this k can take values from 1 to h minus 1. So this is not one equation. So if I have k is equal to 1, I get one equation. If I plug in k is equal to 2, I get second equation, and so on. So this is a system of equations. There are exactly h minus 1 equations, and we need to determine h minus 1 betas here, right? So this is a system of linear equations, and it's quite easy to solve this to obtain betas. So how do we actually solve for this? So first of all, we know that, so there is this absolute value of k minus j here. And we know that autocovariance of -1 and 1 is the same thing, so we can ignore this absolute value sign, nothing changes. Before I proceed, why do we have absolute value of k minus j? So if you, so when you write this, right, so expected value of xt plus h minus j and t plus h minus k is going to be, right, your gamma of this minus this. Now it's possible that this could be 1 and this entire thing could be 2, and in that case it would be gamma 1 minus 2. It's also possible that this first thing can be 2 and this can be 1, so it can be gamma 2 minus 1, right? So basically this can be positive or negative, but the sign doesn't matter, so you can write this absolute value here. Or we can even not write the absolute value, okay? Right? Why? Because it's a symmetric, gamma is a symmetric function. Okay, so to see that this is a system of equations, I have actually written down all of the equations that are here. Okay, so k is equal to 1 is this guy. If I plug in k is equal to 1, I get this first row multiplied by this vector. K is equal to 2, then the second row multiplied by this vector. Okay, so this system of equations can be written out in form of vectors and matrices in this form. This vector, I'm calling it as gamma h minus 1 because it has h minus 1 components. This is a square matrix. This is a vector again. So this should give you an idea of how to solve for this equation, right? So if this is invertible, you put this on the other side and then you have your solution. So again, we're going to write this system of equations in another more convenient form. So gamma h minus 1, right, times this matrix times this vector. And now a more convenient way to write out that entire matrix is this. So what does this mean? So this means that each element has this form. So I have a h minus 1 times h minus 1 matrix, right? That's the dimension of the matrix. So each element, so say I want the element in the first row, second column. So I will be 1 and J will be 2. So the element in the first row and the second column will be gamma 1 minus 2, right? So this is a very convenient way of writing that entire big matrix. Make sure you open this out and that this notation makes sense to you. So if this gamma is invertible, then it's easy. We know what all the betas are. So like I mentioned earlier, this is the other problem, right? We're predicting this current value based on the future values. I have told you that the betas will be the same. However, you will go through the exercise of obtaining a solution for this in the homework. And you'll see that you'll end up with the same answer. Okay, so what do we do with regression? Okay, so we'll be using that in this idea of partial correlation between x, y, and z. So we have three variables, x, y, and z, and both x and y are related to z's, right? And basically, I want to find correlation between x and y that takes into account this variable z. So x and y are three variables. The partial correlation between x and y given z is obtained by, so we first regress x on z and we get x hat. Then we will regress y on z and get y hat, and then calculate the correlation between these two quantities. So what this does is it measures the correlation between x and y, but after removing the linear effect of z. So remember I said z is affecting both of these, and I want to remove this effect. So I want to calculate correlation after removing this effect, and that's exactly what partial correlation does. So this is the partial correlation between x and y given z. So we will be using this idea to define to define the partial autocorrelation function. So we have this predicted value of xt plus h, and this is based on all of these points. It is very, very important that you are familiar with this definition of x hat t plus h. So regression of x hat t plus h on all of these variables, we know how that looks like, right? And so now we want to regress xt based on these future h minus 1 variables. So this is based on past h minus 1 variables, xt is based on future h minus 1 variables. We know that the coefficients for the two are going to be the same, okay? So we have the predicted values. So now the PACF of a stationary process xt. This is the notation phi, and there are two h's here. Why do we use double subscripts? You'll probably find this out next week. Okay, so for now, stick to the two subscripts. So this is a notation for PACF. These h takes values 1, 2, and so on. So phi 1, 1, right, is just correlation between xt plus 1 and t. This is just rho 1, okay, so nothing new here. For phi HH, where h is greater than or equal to 2, it's basically correlation between this. So it's xt plus h minus predicted value of xt plus h and xt minus predicted value of xt, okay? So basically we are looking at correlation between xt plus h and xt after removing the effect of all of these variables, right? So again, correlation between xt plus h and xt after removing the effect of all of these variables. So let's look at the PACF for AR1 process. This is the AR1 process. I'm assuming phi is less than 1, so we're all good here. So the covariance, so before the PACF, let's see the covariance between xt and xt minus 2, right? So this is lag 2, right? Is this, it's non-zero. Now let's look at the partial autocorrelation function. That is the correlation between these 2 points after we remove the effect of xt minus 1, okay? So if you want to remove the effect of xt minus 1, we will be regressing xt on xt minus 1 and xt minus 2 on xt minus 1, right? Remember, this is the effect we want to remove. So two regressions, xt on xt minus 1, t minus 2 on t minus 1, okay? So regression of xt on xt minus 1 is this, and t minus 2 on t minus 1 has this form, but we know that the constants beta 1, beta 2 are the same. Moreover, we've already proved at the start that for this one time step difference, right, there's only one time step difference here, this beta turns out to be rho 1. And for AR1, this rho 1 is this phi. So it is very important now that you're familiar with the ACF of the AR1 and the MA1 processes. Actually, even the MAQ process, not just the MA1. Yeah. So we know that, so there's a hat missing here. So let me go ahead and, okay, I'm not able to edit this. So x hat is phi times xt minus 1 and xt minus 2 hat is this. So now if I look at the covariance, right, covariance between these two, why? So correlation is just covariance divided by the standard deviation. So I'm looking at the covariance first. So this, I'm plugging in the values of xt hat and xt minus 2 hat, and we get this, right? So xt minus 1, phi xt minus 1 is wt. So I have wt, xt minus 2, and phi xt minus 1. So now if you remember, so if you plug in, or if you remember the results of causality, right, this xt minus 2 is going to be dependent on t minus 2, wt minus 1, and all the previous white noise. Xt minus 1 is going to depend on wt minus 1 and all the earlier white noise. So basically, wt is independent of or uncorrelated with xt minus 2 and phi xt minus 1. So you have to think a little bit about this, right? So if you xt minus 2, think about the causality of AR processes, right? Or if you simply just plug in, so xt minus 2 will be what? Phi xt minus 3 plus w xt minus 2, right? So wtx minus 2, and this is uncorrelated. So anyways, so we get that the correlation, covariance is 0, therefore correlation is 0. So for AR1, the ACF2 wasn't 0. However, the PACF at lag 2 is 0. So now we take a look at a more general ARP process. So this is the ARP process, and we're assuming that the root of this polynomial are outside the unit circle, right? So basically this is causal. And what trick am I using here? So I'm multiplying this with xt plus h minus k and all of these terms with xt plus h minus k and taking expected values. We get this. So we have done this trick once before. So we get this system of equations, right? So for an ARP process, right, phi 1, phi 2, phi p, basically this satisfied this system of equations. Why am I calling it system? Because k can go from 1 to p. Okay, so now let's look at, so in order to look at PACF of an ARP process, we need to look at the predicted value of x t plus h, and specifically we are going to look at regression of xt plus h on all of these points for h greater than p. Why h greater than p? Because we are going to try and show that the covariance of the PACF of this ARP process is 0 if the lag is greater than p. That's why we're looking at h greater than p. So okay, so we need to look at this regression. We know that this is a prediction error. There are again typos here. All of these signs should have been minus. Okay, so we take derivatives with respect to bk, right, and equate to 0. So this is what we get. So this is the system of equations again. So this is pretty much similar to the system of equations we wrote earlier. Okay, so I'm not going to go into the details of all of those. But remember, k now goes from 1 to h minus 1, right? We have those h minus 1 terms now. So this is what we get. So we want to determine beta such that this system of equations is satisfied. But we know this is an ARP process. So gamma p plus 1 onwards, all of these terms are 0. So what are we left with? We are left with this system. Gamma k is equal to all of this, k going from 1 to p. So basically we have, this is a system of equations with a p system of equations, right? There are p equations and p unknowns. So we want to determine beta that will solve this. Recall from the previous slide that that phi's satisfy this equation, right? So we want to find numbers that satisfy this equation, right? We want to find betas that satisfy this equation, but we already know that phi satisfy this equation. So basically, beta 1 is phi 1, and so on till beta p is equal to phi p. That's what we get. So basically what we get is the predicted value of xt plus h is based on or has this form. Okay. So now we are ready to look at the autocovariance, the partial or the PACF. So we know that PACF has this formula, right? And xt plus h minus x hat xt plus h, that is this minus, this is going to be wt plus h, right? This is basically from because x is an ARP process. And now, because we are assuming that because this process is also causal, xt is going to, and xt predicted value are going to depend on only all of these white noise terms. right? So basically WT plus H is uncorrelated with all of these terms, and therefore phi HH is 0 for H greater than P. So what we get is PACF for autoregressive processes is for ARP process falls off after P lags. For less than P lags, however, it need not be 0, okay? So just a quick exercise. If I were to ask you what is this process, right, what would be your guess? This is the ACF and this is the PACF. So if you're thinking this is an autoregressive process, you are right? Because the PACF falls off, the ACF doesn't. And I think this is probably AR2. So this is a real data application. So at the start of the course, we looked at this data which had the El Nino and fish population. And this is the plot of the recruitment series. And you can see that this ACF doesn't fall off, but this PACF does. So this probably is an autoregressive process. So that is all in this video. In the next video, we shall take a look at forecasting. So since you've already seen how to predict future values, that's exactly what we do in forecasting. So not a whole lot of new things to study in the next video. All right, that's all for this one. See ya.